Hello everyone, my name is Shu Xiaoming. In this project, I will use machine learning methods to explore merchant materials with a specific focus on iron meteorite. Well, colonized Mars has been human dream for past decades, and because Mars represents a new frontier for human exploration. However, it is hard to establish a human presence because that requires sustainable living conditions and infrastructures. And also in this project, such a big project, material is an important issue. We can either identify and utilize low commercial materials or utilize materials like iron meteorite. So in this project, I will explore how the machine learning method could help people identify, analyze, and evaluate merchant material and or the meteorites, which may suggest how human could utilize them. Okay, so here's the outline of the project. I will first analyze the classification of merchant minerals based on its chemical composition. And second part is the background of iron meteorite. The third part is recognize different phases in the iron meteorite's microstructure. And the last part is based on the point 2 and point 3, build a new type of data frame of iron meteorite to see how different factors affect the mechanical properties. So let's begin the first part. Well, NASA has sent some Martian rovers to Mars, and this Martian rover usually carries some advanced instruments. And one of the instruments called Alpha Particle X-ray Spectrometer, or APXS. The APXS will emit alpha particles to a sample, to a manual sample, and the sample will emit X-rays. So by analyzing the X-ray pattern, we will know the distribution of the compounds in such a manual. So here's the data set that we're going to use. The data set is come from a geology journal about manuals on Mars. The data set sets 9 classifications of merchant manuals based on their composition. This data sets or these categories are written ahead of each of the data. For example, this block of data belong to a category called basaltic soils, and these three rows belong to a category called plant basalt. And there are 9 categories in total, and the picture shown here is 1/5 of them. The method we use for analyze the manual composition data is neural network, which composed of input layer, hidden layers, and the softmax layer. The input layer use the data we just show in data from, and by some mathematical manipulations, the input data will transform to a new data set in the hidden layer. There may be more than 1 hidden layers, and in that case, the output from the previous hidden layer will serve as input in the following hidden layer. And then the data was transferred to a layer called softmax. The softmax will show the possibility of each categories, which in this case is the manual type. So suppose we have a new data set and put it in neural network, that will show the softmax layer will show the probabilities of how it think the new composition belong to. So what kind of manuals does the new data set belong to, and he make predictions based on the possibilities in the softmax layer. So basically the type with the largest possibility. So here's the structure of neural network and the result. Our neural network composed of input layer, 2 hidden layer, and 1 softmax layer. The training data we use is 80% of data set, and the testing data we use 20% of the data set. The result is, I think it's pretty good. We have a 0.47 test loss, and the test accuracy is 0.87. So here's an example showing how we use the model to make some new prediction. So suppose we have a new minor with composition compounds like this. And then we use the model, we put the data in the model, and that will predict the manual category. So in this case, for example, the prediction is the basaltic soil. So part two is about the background in iron meteorites. So iron meteorites takes up 4 to 5% of all meteorites and are primarily composed of iron nickel alloys. And among them, the nickel content usually ranges from 5% to 70%. So one of the most common thing iron meteorite is octahydrite, which composed of carbonate and titanite. The carbonate usually have a very low nickel concentration, ranging from 0 to 5 maybe, or 0 to 7. And titanite usually have a high nickel concentration, usually from 20% to 50%. And when the nickel concentration is about 50%, there will be a new form called tetratenite. So in this project, we put the titanite and tetratenite together because they have relatively similar compositions and the mechanical property. So now let's see how this physics looks like in a microstructure. So here's the PEM image. The carbonate is the dark side, the dark part of the image, and the titanite and tetratenite is the lighter part of the image. So actually the strip-like carbonate and titanite will form a phase called placet, but here we separate the placet into the titanite and carbonate. Also, there's a special region called cloudy zone, which is microstructural features formed during slow cooling of the titanite. So basically, in this algorithm, we're gonna classify these three phases just from the XPEM image. So here's the data set. The XPEM images are took from the samples called Toluca and Odessa. These are two meteorites. And the method we use here called the grid value method. In machine learning, grid value refers to the intensity level of a pixel in grayscale image, typically ranging from 0, which means completely black, to 255, which means completely white. So at first, a screenshot was taken on each of the carbonate, cloudy zone, and tetratenite plus titanite phase to see their grid value range. And we will use that grid value range as a filter to identify the phases in the image. So here's the result. The first picture shows the original image, and then it maps the region the algorithm think the carbonate, cloudy zone, and titanite phase mapped by the white color. So in this slide, we have the sample A and the sample B. And the fractions of each phase was shown here. For example, the carbonate fraction is 0.16, and cloudy zone is 0.54, and titanite is 0.2 for the sample B. So here's a similar result for the sample C and sample D. Yeah, this mask should look reasonable. So, well, in this part specifically, because we don't have the precise data in the article, we cannot determine exactly or area proportion of each phase. So there are definitely some methods such as the point counting method that can also estimate the phase fraction. But because those methods are still not very precise, so we didn't apply here and make comparisons. So just based on the manual estimation, the accuracy of this grid value method is over 80%, as you may see from the result part. So I will temporarily stop here because the time limit of the final project. So for this project, I want to appreciate Professor Donat's group for the research in alloys and the metal structure, and also my mentor, Samantha Manners, for her research specifically on the iron nickel alloys and the meteorites. And here's the reference. So there are other parts in this project, and I will also record it and upload. But for the final project part, you can grade it based on the part I recorded this video. Okay, thank you.